You may already know about subatomic particles and the basic atomic model, but you may not know about the history and the discovery of the three subatomic particles. So what are subatomic particles? Well, let's pull up a 3D model of a basic atom. The three subatomic particles are the proton, which is in the nucleus, the neutron, which is also in the nucleus, with an equal number of neutrons and protons, and electrons, which orbit around the nucleus. The charges of these subatomic particles are positive, 0, and negative, respectively, with neutrons and protons having a very similar mass, and electrons having almost no mass. Before we dive into the discovery of subatomic particles, however, we must understand the first general atomic theory, Dalton's atomic theory. Stated by English chemist John Dalton in 1803, it consists of four basic postulates. That 1, elements consist of indivisible small particles, or atoms. 2, that all atoms of the same element are identical and that different elements have different types of atom. 3, that atoms can neither be created nor destroyed. And 4, that compound elements, or compounds, are formed when atoms of different elements join at simple ratios to form compound atoms, or molecules. This did lead to a question, however. Are atoms divisible? In the late 19th century, physicist J.J. Thomson began experimenting with cathode ray tubes. A cathode ray tube is a sealed glass tube from which most of the air has been evacuated. A high voltage is applied across two electrodes at one end of the tube, which causes a beam of particles to flow from the cathode to the anode. The tubes are called cathode ray tubes because a particle beam or cathode ray originates at the cathode. The ray can be detected by painting a material known as phosphors onto the far end of the tube beyond the anode. The phosphors spark or emit light when impacted by the cathode ray. This is extremely similar to how CRT televisions, or cathode ray tube televisions, operate to produce an image on a screen. To test the properties of the particles, Thomson placed two oppositely charged electric plates around the cathode ray. The cathode ray was deflected away from the negatively charged electric plate and towards the positively charged plate. This indicated that the cathode ray was composed of negatively charged particles. Thomson also placed two magnets on either side of the tube and observed that this magnetic field also deflected the cathode ray. The results of these experiments helped Thomson determine the mass-to-charge ratio of the cathode ray particles, which led to a fascinating discovery. The mass of each particle was much, much smaller than that of any known atom. Thomson repeated his experiments using different metals as electrode materials and found that the properties of the cathode ray remained constant no matter what cathode material they originated from. From this evidence, Thomson made the following conclusions. That the cathode ray is composed of negatively charged particles, the particles must exist as part of the atom since the mass of each particle is only a fraction of the mass of a hydrogen atom, and that these subatomic particles can be found within all atoms of all elements. Since he knew that the atoms had an overall neutral charge, Thomson theorized that there must be a source of positive charge within the atom to counterbalance the negative charge on the electrons. This led Thomson to propose that atoms could be described as negative particles floating within a soup of diffused positive charge. This model is often called the plum pudding model of the atom, due to the fact that its description is very similar to plum pudding, a popular English dessert. The next groundbreaking experiment in the history of the atom was performed by Ernest Rutherford, a physicist from New Zealand. In his famous gold foil experiment, Rutherford fired a thin beam of alpha particles at a very thin sheet of pure gold. Alpha particles are helium nuclei that are given off by various radioactive decay processes. In this case, Rutherford placed a small sample of radium, which is a radioactive metal, inside a lead box with a small pinhole in it. Most of the radiation was absorbed by the lead, but a thin beam of alpha particles escaped out of the pinhole in the direction of the gold foil. The gold foil was surrounded by a detector screen that would flash when hit by an alpha particle. Based on Thomson's plum pudding model, Rutherford predicted that most of the alpha particles would pass straight through the gold foil. This is because the positive charge in the plum pudding model was assumed to be spread out evenly throughout the entire volume of the atom. Therefore, the electric field from the positively charged soup would be too weak to significantly affect the path of the relatively massive and fast-moving alpha particles. However, the results of this experiment were striking. While almost all the alpha particles passed straight through the gold foil, a few alpha particles, or about 1 in 20,000, were deflected more than 90 degrees away from their path. Rutherford himself described the results with the following analogy: "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Based on his experimental results, Rutherford made the following conclusions about the structure of the atom. That 1. The positive charge must be localized over a very small volume of the atom, which also contains most of the atom's mass. This explained how a very small fraction of the alpha particles were deflected drastically, presumably due to the rare collision with the gold nucleus. Since most of the alpha particles pass straight through the gold foil, the atom must be made up of mostly empty space. This led Rutherford to propose the nuclear model, in which an atom consists of a very small positively charged nucleus surrounded by the negatively charged electrons. Based on the number of alpha particles deflected in his experiment, Rutherford calculated that the nucleus only took up a tiny fraction of the volume of the atom while making up a majority of the mass. However, this nuclear model is not the end-all be-all of the atomic model. Physicists such as Niels Bohr would continue to design experiments to test the nuclear model of the atom, which would eventually evolve into the modern quantum mechanical model. But there's a problem. You see, we had been able to measure the mass of the proton and the electron and of the entire atom, but there was a discrepancy. Take helium, for example, with an atomic number of 2, meaning that it has 2 protons that contribute 2 mu to the mass, but an atomic mass of 4. Where was that 2 mu coming from? In 1932, French physicists Frédéric and Irène Joliot-Curie bombarded beryllium with alpha particles and observed that an unknown radiation was released that in turn ejected protons from the nuclei of various substances, in this case a paraffin wax target. They also found that these protons recoiled with very high velocity. Joliot-Curie believed that the radiation hitting the paraffin target must be high-energy gamma photons, but James Chadwick, an English physicist, thought that explanation didn't fit. Photons having no mass wouldn't knock loose particles as heavy as protons from the target. In 1932, he tried similar experiments himself and became convinced that the radiation ejected by the beryllium was in fact a neutral particle about the mass of a proton. He also tried other targets in addition to the paraffin wax, including helium, nitrogen, and lithium, which helped him determine that the mass of the new particle was just slightly more than that of the proton. Chadwick also noted that because the neutrons had no charge, they penetrated much further into a target than protons would. Chadwick would come to the following conclusions in his February 1932 paper. That 1. This radiation is composed of particles of about the mass of a proton, or about 1 mu. That this radiation is composed of neutral particles, and that this radiation is composed of a third subatomic particle named the neutron. The quest for the 3 basic subatomic particles was complete.